All right. So we have a lot of things to talk about with regards to induction motors today. So our first little topic is going to be the development of rotating magnetic fields in the stator. Right. So let's consider a relatively simple stator cross section. Bear with me as I try to draw circles. So I'm going to make this relatively simple by having a three-phase, two-pole stator. So our A windings will be these guys in black. So this is going to be A, and this one is going to be A prime. So effectively, if current is flowing into the A portion, it'll be flowing out of the A prime, 120 degrees out of phase with the A winding. We should have our B and B prime. And 120 degrees out of phase with our B winding. We'll have our C and C prime. All right, so I am, I'm going to make my life slightly easier and perhaps you guys is slightly miserable here in a moment by making a copy of this so that I don't have to redraw it over and over and over again. So our three windings will each carry a sinusoidally varying current. Where the current in the A windings, IA of T, will be whatever the amplitude of our current waveform is, which I'm just calling I sub M, cosine omega T. I'm going to say that our B phase current is IM cosine omega T minus 120 degrees. And similarly, our C phase current will be IM cosine omega T minus 240 degrees. So effectively, we have a positive phase sequence. We are making an assumption here that our voltage source that's connected to our stator is a balanced three-phase source, which it has to be unless we physically do something to make it not be. And we are assuming that the load that our induction motor represents is also a balanced three-phase load, which it will be, assuming all of the windings have the same, resistance, reactance, and all that kind of good stuff, which they should because they're made by robots nowadays. Okay. All right. So what I'm going to try to do here is make a plot of these three currents as a function of time. So let's call this value IM, this value negative IM. We're going to start at T sub 0 and then look at things at T1, T2, T3, and T4. Because our initial phase angle is 0 degrees, sorry, IA is black. My A phase current should look something like this. My B phase current, let's see, is going to look something like this. And my C phase current is going to look something like this. Okay. So imagine those were pretty looking sinusoids and not wiggling looking sinusoids because I can't hold my hand steady enough to draw them well. You guys should get the gist of things. And I'm going to extrapolate these things a little bit further here. No, what did I just cancel? All right, so what we are going to do is we are going to effectively evaluate these currents at the instances in time that I've indicated on this figure. So at T is T naught, we effectively have a phase angle of 0. And then at some later point in time, we can see that our phase angle is effectively 90 degrees, then 180, then 270, all the way back to 360. So at T is equal to T naught, the value of the phase currents is, so IA at T naught is at its maximum. Right. IB is going to have a value of negative its maximum divided by 2. And similarly, IC at T naught will also have a value of negative its maximum over 2. So what do we know about the, actually, before we do that, I'm going to paste my stator diagram here, and we're going to look at some things. Okay. So let's start with our A phase. So let's say, for the sake of argument, that positive current is going to be directed out of the board. So our A phase current has a value of IM, so it's going to be out. And then our A prime wire is going to be directed into the board, like so. And it's going to have some particular magnitude that's IM, right? Well, our B and C phases are negative. So that means B is going to have a current flowing into the board. B prime will be out of the board. Likewise, C will be into the board, and C prime will be out of the board because of the direction or the sign on those currents. Okay. So what do you guys remember about the strength and direction of magnetic fields and how they relate to currents? This is one of the first things that we talked about in this class. Probably talked about it too damn long for most of you guys' interest level. But now it's coming back to us, right? So if the current is at its maximum, the magnetic field strength will also be at its maximum because they are proportional to each other. Now, what did we learn about the direction? Well, that was the right-hand rule, right? So using the right-hand rule, we can figure out what the direction of our magnetic field is. So let's talk about the magnetic direction, or excuse me, the direction of the magnetic field that's caused by the A winding here, right? So the way that I'm looking at it, it's coming out of the board up here and going into the board down here, and my thumb tells me the direction of the field. So my field should be directed to the left, okay? So from this center point, I'm going to have a magnetic field BA directed to the right. Now, we're going to do the same thing for the magnetic field caused by the B phase winding and the magnetic field caused by the C phase winding, right? So for the B phase winding, effectively we have the same thing, except it's just rotated slightly, which means our magnetic field is going to be rotated slightly as well. It's not going to be as strong because the current isn't as strong. So we're going to see something smaller. This, and if we look at our C phase magnetic field, we're going to have something like that. Okay. The angle formed between the C phase and the A phase is going to be exactly 60 degrees, and the angle formed between the A phase and the B phase is going to be negative 60 degrees. So what happens if I add all three of these together? All of the horizontal parts are going to add together, and all of the vertical parts are going to add together, right? But our vertical parts are in opposite directions, so they're going to wind up canceling out. So we're going to have a total magnetic field that is directed to the right, and it will have a particular value, okay? So our net magnetic field is going to be whatever BA is, we'll get to that in a minute, plus the strength of BA. So I'm saying that since coil A has a current of IM and coil B has a current of magnitude IM over 2, the strength of that magnetic field should be half as large. And then we're going to have cosine of minus 60 degrees. And then we're going to have another 1/2 BA times cosine positive 60 degrees. So that's giving us only our horizontal components. And when we add all of those together, we get 3/2 times the field strength generated by coil A, all directed to the right. So now let's look at what happens at our time T1, okay? So at T1, coil A is carrying no current whatsoever. B is going to be at whatever value it has when we evaluate this thing at 90 degrees, and C will be the same thing, IM times the cosine of 90 minus 240. So we're going to have IA of T1 is 0. IB of T1 is going to come out to be the square root of 3 over 2 times IM. And IC will come out to be negative the square root of 3 over 2 of IM. So if we look at our stator winding once again, no current is flowing in the A phase, so I'm going to leave both of those blank, right? Our B phase is carrying a positive current. So we're going to put a dot in the middle of B and a cross in B prime. Our C phase is carrying negative current, so C prime is going to have a dot and C is going to have a cross. So what are our fields going to look like? Well, our field due to the A coil is going to be 0. So there's no contributing thing there, right? If we look at our B coil, right, it's going to be directed diagonally up and to the left. And if we look at our C coil, it's going to be up and to the right. And these form 30-degree angles with this vertical axis. So what we're going to wind up getting is a net field that is 0, so that's the contribution from the A coil, plus root 3 over 2 let's call this BM for the maximum field strength, which would occur when our current is IM, times the cosine of 30 degrees. And then we're going to add to that square root of 3 over 2 BM cosine negative 30 degrees. And this comes out to be, when we add all three of them together, 3/2 BM directed straight up. So our net field in this case was directed to the right. In this case, it's directed straight up. They have the exact same magnitudes, right? So the field strength stayed the same, but its direction changed. So what do you guys think is going to happen when we move along to time T2? Turned 180 degrees, actually. So exactly the same as T0, but turned 180 degrees, because our current in phase A has gone from positive IM to negative IM. So it's 108, all our currents are going to be 180 degrees out of phase because we're half a cycle later. Right, so at T2, we're going to have the exact same thing that we had at T0. So the strength is going to be 3/2 maximum value of B, but it's going to be directed to the left. What do you think is going to happen at T3? So T3 is just T1, but 180 degrees out of phase. So it's going to be the exact same thing, but directed down. If we looked at any other value of time, what we're going to find is that our field strength is constant, but its direction is just slightly skewed. So as our currents cycle, we have a field strength that has some maximum value starting here at 0 degrees and then slowly rotating around our stator. So from these results, we can say that A three-phase stator winding, which carries currents that are 120 degrees out of phase with each other, results in a magnetic field whose amplitude is constant, but varies in space as it rotates counterclockwise around our stator. So if we connect our three-phase winding, let me go to the next page here. So if we connect our three-phase winding to the currents IA, IB, and IC that we have indicated previously, what we're going to wind up having as a B field that is 3/2 BM, but it's rotating at some speed omega in the counterclockwise direction. So let me ask you guys a slightly different question here. What would happen if I swapped my B phase and my C phase? Or really, what would happen if I swapped any two phases? So if I swap any two of these phases, I go from having a positive phase sequence to a negative phase sequence. Did you guys learn what the difference between a positive phase sequence and a negative phase sequence was in your circuits class? Okay, so effectively, all that would happen is that the directions of our B and C phase currents would be opposite, which means we're going to wind up getting rotation in the opposite direction. That's it. It's going to do us the exact same thing, except that the rotation is going to occur in a clockwise direction if we swap two of the phases. Everything else will remain exactly the same. All right, so how do you guys feel about the presence of a rotating magnetic field caused by our stator? Makes reasonable sense, right? So now let's talk about how that rotating field causes our rotor to turn, or how an induction motor actually works. So we'll call this little part generation of induced torque. On our rotor. So now I'm going to draw a picture of a cross section of our rotor windings, or it could be a squirrel cage. Actually, let's say that this is a squirrel cage thing. It'll be slightly easier to understand. So this is the end ring of our rotor, and its job is to short out our conductors, right? So let's say that we have a conductor here directed into the page and another conductor here directed into the page. There are also going to be other conductors around the ring, but we're not going to worry about them right now. Let's just pretend that we have a single conductor on one side and a single conductor on the other side, and we'll let all the other stuff work itself out, right? So this is a conducting bar, and this is also a conducting bar. Well, we know that our stator is generating some B field, so I'm going to call this B sub S for the stator, and that B field is rotating with an angular velocity omega sub S. Okay. So let's assume that to begin, our rotor or the conductors in our rotor, are stationary. They are not moving at all. What is the rotor seeing? It's seeing a magnetic field whose value changes in space, right? So effectively, with the orientation that we have at this snapshot in time, the flux that's passing through the loop that's formed by our conducting bars being shorted out by our end rings is zero. Okay, because the magnetic field is directed in the same direction as the surface of our loop, effectively. As our B field rotates, our flux seen by our conducting loop starts to increase, right? So it's starting at zero and it's getting larger and larger and larger until a point where our B field is at 90 degrees and then the flux is at its maximum, and then our flux starts to decrease until it's zero, and that repeats over and over and over again. Well, what happens if we have a conducting loop in the presence of a time varying magnetic field? Inductions, absolutely right. So we're going to induce some voltage. So our induced voltage, E, is going to be equal to the cross product of our relative velocity. I'll talk about that in a moment. Crossed into our magnetic field, and this is dotted into L. Okay. So relative velocity. Between our stator field, B sub S, and our rotor. Well, since our rotor is stationary right now, our relative velocity is just the speed at which our B field is rotating. This length here is just the length of one of our conducting bars. Okay. So effectively, what this says is we are going to induce some voltage drop across our conducting bar. Because our conducting bars form a closed loop, that voltage will in turn drive some current, which is what Patrick suggested. Okay. So we are going to have some current flowing through our conductive bars. So let's say, for the sake of argument, that the induced current has these directions, right? So flowing out of the board on the top conductor and into the board on the bottom conductor. We don't actually have to assume anything. Lenz's law tells us what direction our current is going to flow, right? So our current is going to flow in such a direction that the induced current will create a magnetic field that tries to keep the flux constant, right? So as we have it right now, our stator flux is increasing because of the way that our thing is rotating. So our magnetic field generated by induction should be in the opposite direction to try to keep that stator, or excuse me, to keep the overall flux small, which gives us a current in the directions that I've indicated here. All right. So what happens when I have a current carrying conductor in the presence of a magnetic field? You guys heard of the Lorentz Force Law before? Okay. So the Lorentz Force Law essentially states that there will be a force generated whenever we have charge moving in the presence of a magnetic field. And that force is going to be equal to Q times V crossed into B. Well, in this case, it's our stator field that's acting on our conductor bars. And this direction V, so actually let's talk about what Q times V is, okay? So charge times velocity, what do you guys think that is? So what do we have when we have charges moving? Current. So Q times V is literally just current times the direction the current is flowing in. Okay. So we could write this as I, L, where L is just giving us the direction of current, crossed into our stator magnetic field, B. So let's look at our top conductor here. Our current is directed out of the board. Our magnetic field is directed up. What should the direction of our force be? Well, this is another place where we apply our right-hand rule, okay? So if our current is coming out of the board, that's where we use our index finger. Our middle finger is the direction of the B field, so it's directed up. And our thumb gives us the direction of the force. So in this case, our force should be directed to the left. So this is our induced force. And so if we look at our picture, we're going to see that our magnetic field is causing some force to be applied to this conductor in this direction. Now, what happens if we look at our bottom conductor? Right, so we have IL directed into the page. Our B field is still up. So what direction should our force be? To the right. So on our bottom conductor down here, the Lorentz Force Law is directed, or the Lorentz force, excuse me, is directed to the right. So what happens if I have a structure like this, and at the top, I'm pulling it to the left, and to the bottom, I'm pulling it to the right? I start to turn it, right? So I have induced rotation. Okay. So because these forces are in opposite direction, they are going to cause the rotor to start spinning, and the rotor is going to spin in the same direction as our rotating magnetic field. So effectively, the rotor is just constantly trying to catch up to the stator's magnetic field so that it can maintain a constant amount of flux passing through that loop. That's all the rotor is doing. It's just spinning as fast as it can possibly spin in order to catch up and keep that flux constant. So that begs the question, what is the fundamental limit on how fast our rotor can spin? Anybody have any thoughts? So if our B field is spinning at some particular speed, the best the rotor can do is the same thing as the B field, right? It'll never get past it. If it ever gets past it, that means we've had to add mechanical power to cause it to speed up and overpass it, right? So the fundamental limitation of our rotor speed is our stator speed effectively. So this is one of the relationships that I gave you guys in that PowerPoint lecture. Our synchronous speed, or our stator speed, is 120 F1 divided by P, where quantity F1 is the excitation frequency of the stator, and P is the number of poles. Okay. So one thing actually that I don't think I remembered to mention here, when I first introduced this last Thursday, is that our stator speed, or our synchronous speed here, is measured in revolutions per minute. So this is probably going to give you some indication as to why we get the speeds that we get, right? So if I have a three-phase, two-pole stator, I'm going to get, or here in the US, I'm going to get a speed of 3,600 revolutions per minute, which means it completes 60 cycles in a second, which is exactly what 60 hertz means, right? If I have more poles, it winds up spinning slower. That's all that's going on here, okay? All right, so our synchronous speed is the fundamental limit, but our rotor can't ever actually get to our synchronous speed, and that's very important, okay? So if, let's say, NS is going to be our stator field speed, also known as our synchronous speed. And M is our rotor speed, measured in revolutions per minute as well. So what would happen if Nm were exactly equal to Ns, meaning that our rotor spun at the exact same speed as our stator field? What do you think the relative velocity between our rotor and stator would be? So if they're both spinning at the same speed, their relative velocity is 0. Well, if their relative velocity is 0, what's the voltage induced on our conductors? 0. If the voltage induced on our conductors is 0, what's the current flowing through our conductors? 0. If there's no current flowing through our conductor, how much force acts on our conductor? Also 0. So effectively, if there's not a difference in speed, we don't generate a torque. So it's critically important, actually, that our rotor never catches up to our stator. Right. So for our device to be operating correctly, we must have NS greater than Nm for motor operation. And we're going to talk a bit more about this by talking about the concept of slip. So let me know when I can go to the next page, you guys that are writing stuff down. All right. So let's talk about slip speed and slip, right? So the slip speed of an induction motor is defined as the difference between the stator, or let's call it synchronous speed, that's less words, so we can say that N slip measured in revolutions per minute is simply our synchronous speed minus our rotor speed. Sorry, this should be NM. Okay. So this is what our slip speed is. Pretty straightforward. It's just the difference in speeds between our rotor and our stator field. Okay. The term slip describes the relative difference. Okay, so it's just a fraction effectively. So we're going to say that slip S is NS minus NM over N sub S, which this is obviously a dimensionless quantity because RPM minus RPM over RPMs gives us no units whatsoever. And so this really just tells us effectively what fraction of our synchronous speed does our rotor lag behind, right? We could also write this as omega S minus omega M over omega S, where these omegas are just our angular frequencies for our stator field and our rotor, right? So instead of dealing with things in RPM, we'd be dealing with it in radians per second. Okay. All right, so we can manipulate this expression a little bit. So I can say that N slip is equal to NS minus NM. And looking at our bottom equation here, NS minus NM is just S, our relative slip or our fractional slip, times NS. So rearranging this a little further, NM, my rotor speed, is just NS minus S times NS, or NS, my synchronous speed, times 1 minus my slip. So again, this is nothing more than saying our rotor spins at some portion of our synchronous speed. But expressed in this way, we can get some ideas about what's happening at different values of slip. Okay, so what happens if S, our relative slip, is equal to 0? What does this imply? Well, in this case, that means NM must be equal to NS. So we have no induced voltages or currents, and so our rotor will decelerate itself in order to generate some torque. Okay. A second case that we can look at is if our slip is equal to 1 or 100%. So what does this mean? Exactly right, no movement. NM is equal to 0, or our rotor isn't moving. So whenever we start an induction motor, our slip starts at 1 and then decreases down to its steady state operating condition, which is usually somewhere between 1 and 10%. If our slip is between 0 and 1, this means our rotor speed is less than our synchronous speed, and our induction motor is in the motoring region of operation. So effectively, all this means is that the device is working exactly how we expect it to. The rotor isn't spinning quite as fast as the stator field is. Everything is groovy. Let's look at a fourth condition. If our slip is negative, what are the implications of this? Not quite. So if our slip is negative, then 1 minus s is going to be something that's greater than 1. So that means that Nm, our rotor speed, will be greater than our stator field speed or our synchronous speed, right? So Nm will be greater than Ns. This is only possible if we add mechanical energy into our rotor. So effectively, we are putting mechanical energy into spinning our shaft. In this case, our device is acting like a generator. It's a crappy one. There are very limited applications of induction motors being used as generators, but there are some. And whenever we have an induction motor acting as a generator, our slip is a negative quantity. Now, let's talk about our last thing here. If our slip is greater than 1, this means Nm is less than 0. Does that make sense? How can our rotational speed be less than 0? It's spinning backwards. Absolutely right. So this is where we have spinning backwards, and this is the braking region of operation or the plugging region of operation. So effectively, we are introducing mechanical power in order to cause the motor to stop spinning as quickly as it possibly can. Right. All right. How much space do I have left on this page? I think I have enough. All right. So now we're going to talk about the electrical frequency of our rotor. Okay. So let me explain what I mean by that. Our stator field has an obvious electrical frequency. So what I mean by that specifically is that our stator field is caused because we hooked our stator windings up to a three-phase voltage source, and that three-phase voltage source is operating at some specific frequency, likely 60 hertz here in the United States, 50 hertz in most of Europe. Our rotor's electrical frequency is going to be different than our stator's electrical frequency. Can anybody tell me why? Because they're spinning at different speeds. That is literally it. Because the rotor spins at a different speed than the stator's field, the induced voltages and currents on the rotor will be at a different frequency than the stator, okay? And the thing that relates these two quantities, the electrical field, excuse me, the electrical frequency of the rotor and the electrical frequency of the stator, is the slip. Okay. So the frequency of our rotor, I'm going to call this F2. Is the number of poles times the slip speed over 120. This is literally just our equation for synchronous speed rearranged to give us frequency instead of speed, okay? Well, since N slip is NS minus NM, or S times NS, which we just dealt with here, this relationship. This is our number of poles times our slip times our synchronous speed divided by 120. And so I'm going to do a little bit of manipulation here. I'm just pulling this S out. And so I'm going to have P times NS over 120. And that bit right there is nothing more than our stator frequency. So the electrical frequency of our rotor is simply the product of the slip times the electrical frequency of our stator. This is also called the slip frequency of the machine. Typically speaking, it's going to be small. So if the electrical frequency of our stator is 60 hertz, we should expect our slip frequency to be somewhere in the ballpark of 1 to 3 hertz. Okay. All right. So let's work an example problem relating some of these things. Sorry for kicking whatever that was. So let's say that we have a 50 horsepower, 3-phase, 60 hertz, Y-connected induction motor. Operates at a shaft or rotor speed of almost 900 RPM. At no load. And a speed of 873 RPM at full load. I want us to determine following quantities. A, the number of poles the motor has. B the slip frequency of the motor, and C, we're going to have to talk about this one, the shaft torque of the motor at full load. So I feel pretty strongly that parts A and B here are relatively straightforward, right? So I want you guys to help me out with them. So if I'm looking for the number of poles, anybody have any thoughts on what relationship I might be using? Or actually, let's take this back slightly further. Let's identify exactly what our problem statement is telling us. Let's start there. Casey, what was your question? Well, sure. Tell me what equation you think it is. All right. So NS, our synchronous speed, is equal to 120 F1 over P. We could rearrange that and find that our number of poles is going to be 120 F1 over NS. Absolutely correct, Casey. So that begs the question, what is F1 and what is NS? F1 is 60 hertz, right? So that's the excitation frequency of our motor, or our stator specifically. So I absolutely agree with that. So let's put that. F1 is 60 hertz from our problem statement. How do we get our synchronous speed? So we're given two speeds here, right? We're given a speed at no load, 900 RPMs, or almost 900 RPMs. And we're given a speed at full load. So our no load speed is effectively our synchronous speed, right? The motor is going to spin as fast as it possibly can, so just under our synchronous speed if we don't put any resistance on it. So if it's not struggling to spin, it's going to spin as fast as possible, right? So from our problem statement, our synchronous speed is 900 RPM, and at full load, our rotor speed was 873 RPM, right? So plugging in numbers, we have 120 times 60 over 900. So what's that give me? Eight, absolutely right. 8 poles. So if we had, this is an aside, this isn't part of the problem here, right? So if we're in the United States and we have a 2-pole machine, the synchronous speed is always going to be 3,600 RPM. If we have a 4-pole machine, it's always going to be exactly half that, or 1,800 RPM. If we have an 8-pole machine, it's going to be half that, or 900 RPM. Effectively, we're going to get to a point where we see these things so many times, we're never even going to have to. If we know that it's a 4-pole machine and it's in the US, we know that its synchronous speed is 1,800. We don't have to do the math or anything like that. That's what it works like. Just like in Europe, a 4-pole machine at synchronous speed is 1500 RPMs. It's always going to be that. So you could develop a simple table here and never have to actually use these equations again. It's always going to be some fraction of 3600 RPM. All right, so we got the answer to part A. That's great. Part B, slip frequency. So that's just F2, which we know to be S times F1. Well, how do we get S? Yeah, NS minus NM over NS. So this is going to be, sorry, 900 minus 873 over 900, which comes out to be 0.03. Absolutely right. Yes, ma'am. Correct. Absolutely correct. So we have a 3% slip. So at full load, our rotor spins 3% slower than our synchronous speed. Okay. So what is our slip frequency? 0.03 times 60 hertz comes out to be 1.8 hertz. So our last thing here, I don't know what you guys' background is in the mechanics side of things, but I feel like it's probably reasonably okay. So what's torque? Okay. Absolutely right. Okay, so let's torque is force times some radial distance out. Absolutely right. Okay. I'm not a statics professor, but yeah, I think they're pretty much the same thing. All right. So it's power from a mechanics perspective. Work over time, which is force times linear distance over time. Right? Because force times linear distance is work, work divided by time is power, because power is nothing more than the rate at which energy or work is done, right? So our last relationship here to figure this out, linear distance. Close. So radius times angular velocity times time. So effectively radius times angle gives us the part of the circumference that we're looking for. So the radius times angular velocity multiplied by time, where angular velocity times time is obviously just an angle. The radius times an angle is a distance. So if we put all three of these things together, we're going to find that power is equal to force over radius times radius times angular velocity times time, all over time. Radius cancels, time cancels. Time cancels. Oh, sorry, this shouldn't be torque over radius, force over radius. This should be torque over radius. I did my substitution wrong. So my apologies there. And so we find out that power is torque times angular velocity. So torque is just power divided by angular velocity. We're going to wind up using this a lot because we're going to be figuring out, we put in some amount of power, some amount of electrical power, and we calculate all of our losses. What is the torque produced by our motor? Because that's an important figure of merit for induction motors. We'll get to that in a little bit, okay? So let's look at this thing a little bit more loosely here, all right? So if I want the torque on my shaft, that I need to know the power that's being delivered to my shaft, right? Well, this is a 50 horsepower motor operating at rated load. So I would argue that the power that's being delivered to my shaft is 50 horsepower. And there are 746 watts per horsepower because I like metric units. Now, how do we figure out what my angular velocity of my shaft or rotor is? So we know that our rotor is spinning at 873 revolutions per minute. Angular velocity is measured in what? Radians per second. So I've got to figure out what to throw in here to get the units that I'm looking for, right? So how am I going to get rid of the minutes and get seconds in here? Let's start with the easy thing. Yeah. So 1 minute is equal to 60 seconds. Okay. So now I need to figure out how to get rid of radians, or excuse me, how to get rid of revolutions and introduce radians. That's actually pretty straightforward, right? What's the number there? 2 pi. Absolutely. There are 2 pi radians per revolution. And so I get horsepower cancels horsepower, revolutions cancels revolutions, minutes cancels minutes, radians is a dimensionless quantity. So this is going to give me 408. And the units here are watt seconds. So let's talk about that. So what is a watt times a second? A joule, absolutely. But what is torque usually measured in? Not a joule. Absolutely right. Newton meters, which is the exact same thing as a joule. All right. Okay. Unfortunately for you guys, I'm not done talking. So I think we have some reasonable idea about the basics of things. So now what we're going to do is we're going to develop an equivalent circuit for our induction motor that we can use to analyze things. So on our first day of class, or not our first day of class, on Thursday, right? We talked about how an induction motor transfers energy from the stator to the rotor. How does it do it? Induction. Absolutely correct. How does a transformer transfer energy from the primary to the secondary? Induction. Absolutely correct. So, because the energy conversion mechanism is effectively the same, I am going to expect that our equivalent circuit for an induction motor will effectively be the same thing as an equivalent circuit for our transformer, because as I mentioned last Thursday, an induction motor is nothing more than a transformer where we allow our secondary, which is the rotor, to spin. Okay. So from that, let's look at our stator model. And I'm putting something here that's very important. We're looking at our stator on a per phase basis, okay? So the why I'm bringing that up is because the transformer model that we developed was for a single phase transformer, but our rotor winding is most definitely a three-phase winding, okay? So this is what it's going to look like per phase. And then when we get into all of our power calculations and all that kind of jazz, we're going to have to remember to multiply by 3 to account for all 3 phases. Okay. So the stator is going to look like this. So here is our stator voltage across one phase. We are going to have some resistance R1 in series with some reactance JX1. So out here, I'm going to say that R1 is the resistance of stator winding. Really, this is, sorry, I can't write, save my life today. One phase of the stator winding, and so effectively it represents the copper losses in the coil, just like it did for a transformer, okay? X1 is the reactance of our stator winding, and it represents losses due to flux leakage, just like it did in a transformer. Okay. Then we're going to have our shunt component. So we're going to have our core losses, because remember that our stator is wound on a magnetic core, just like we would see in a transformer. And then we're also going to have some magnetization losses, like so. So core losses. This represents our magnetization losses. And then out here, we have our terminals where our voltage V1 is our terminal voltage. And E1 is our induced voltage. So our stator model literally looks exactly the same as the primary windings of a transformer, okay? The only difference is the size of the parameters, okay? So let's talk about that a little bit. So R1 for our stator is going to be very similar to R1 in our transformer because it's literally just a copper coil, okay? X1, however, is going to be appreciably different, okay? So X1 represents our leakage, right? So in a transformer, we expected our leakage to be pretty small because typically speaking, we're wound on a solid core. But in an induction motor, there will absolutely be an air gap between the rotor and the stator. Therefore, we are going to lose flux due to leakage, right? So we should expect X1 to be significantly larger than what it was for our transformers. Our core resistance, this again just represents eddy current and hysteresis losses in our medium, so that's going to be effectively the same thing. Our air gap magnetization, XM, that's actually going to be smaller, okay? Now that may not make intuitive sense, but our magnetization current, IM, is going to be much larger because the reluctance of our air gap is so much larger than the reluctance of our core. And that larger reluctance means we're going to have a smaller reactance. Okay. So other than those simple things, we should expect X1 to be larger than what we saw in transformers and XM to be smaller than what we saw in transformers. The stator winding of an induction motor is effectively the same thing as the primary winding of a transformer. Okay. Yes, ma'am. I didn't feel like writing stator windings again, so it's just the same thing as above. Yeah. All right. So now let's talk about what's going on with our rotor. Actually, I need to make one small addition here. Our stator model is operating at an excitation frequency of F1, right? Why that's important is because we're about to see in our rotor model, it's operating at an entirely different frequency, which could be problematic. Okay. So here's what our rotor model is going to look like. The induced voltage, E2, is effectively just going to be, it's going to be influenced by the slip, right? Because our slip frequency, so this whole thing is going to be working at F2, is the frequency at which these voltages are being induced. Okay. Now, on this side, we are going to have some reactance, J, S, X2. In series with some resistance R2, where E2 is the induced rotor voltage, R2 represents the rotor resistance per phase. We'll get into that in a moment. And X2 represents the rotor reactance per phase. Okay. And this current I2 is our induced rotor current. All right, so if we employed a little circuit analysis here, we could say that our rotor current I2 is going to be our induced voltage SE2 divided by the total series impedance, which is R2 plus JS X2, where I want to be clear here, our current I2 is at a frequency of F2, our slip frequency. Okay. Now, this equation is a little bit misleading. Okay, let me explain what I mean by that. If we wanted to calculate the power absorbed by our rotor, I'm putting a 3 here because we're dealing with a 3-phase system. Our power is just going to be the magnitude of our current squared times our resistance. Now, why this is problematic is because it infers that our power absorbed by our rotor is independent of the slip that we're experiencing, which cannot be true. Okay. Our slip has to influence what's going on here, right? So effectively, this says that our rotor is going to absorb the exact same amount of power, whether or not it's carrying a load or we're holding it still. Wildly not true. Okay. So what we're going to do instead is we're going to revisit this equation right here. And we're simply going to factor out S from everything. Okay. So we have a factor of S in the numerator. My pen will write here. That we can get rid of. So that's just going to leave us E2, our induced voltage. We're going to have to divide R2 by S. And then we're going to have plus J X2. Where in this case, I2 is effectively now a stator referred quantity, or at least it's operating at our stator frequency. Okay. So if we calculate our power here, I'm giving myself a little bit of space because I'm going to introduce a subscript in a moment. This is going to look like 3 times the magnitude of I2 squared. And the magnitude of I2 is literally not going to change at all, but we're going to have R2 over S now. So we have some dependency on slip, which is exactly what we would expect for proper operation of one of these machines. Now, I'm going to call this the air gap power, because it's the total power that's being transferred across our air gap. Okay. It represents not only copper losses, but also the mechanical power that's being delivered to the rotor, right? So this is going to be P2 copper, or Cu, plus P met. Okay. So our copper losses, or our I squared R losses, we're going to pull them out effectively. Oops, I went slightly too far. So we're going to say that this is 3 times the magnitude of our rotor current times R2 plus R2, sorry, that should be R2, not RS. R2 over S times 1 minus S. So effectively, I've split this thing up into 2 distinct parts. Okay. Let me go to the next page here. So I have Yes, ma'am. You good? All righty. So we're gonna have, sorry, I need my 3 first. I2 squared times R2 plus 3 times the magnitude of I2 squared times RS, dang it, R2 over S times 1 minus S, where this bit right here is the copper losses in our rotor. And this bit right here is the mechanical power delivered to our rotor. So just to summarize these relationships, because we can kind of see what's going on here. Power that's delivered across our air gap is 3 times the magnitude of I2 squared times R2 for S, which is also simply the sum of the copper losses in our rotor plus the mechanical power delivered to our rotor. Our copper losses are 3 times I2 squared times R2. This is nothing more than the slip multiplied by the power delivered across our air gap. And we have our mechanical power, 3 times I2 squared R2 over S times 1 minus S. This is nothing more than 1 minus S times our air gap power. So what I'm going to do now is I'm simply going to combine our rotor equivalent circuit, or excuse me, our stator equivalent circuit with our rotor equivalent circuit referred to the stator side. Because that's typically how these things are analyzed, giving us this complete equivalent circuit. So again, this is on a per phase basis. So here we have R1, JX1, here's RC, JXM, over here is my rotor part. So this is going to be J X2 prime or J A squared X2. And I'm giving you guys something here. This is how it's shown in many textbooks. So I'm showing it to you like this. This is R2 prime. This is R2 prime over S times 1 minus S. So it's just breaking up that resistance on the rotor into the part that attributes to copper losses and the part that attributes to mechanical power, but we can simply lump them together as R2 prime over S, which is nothing more than A squared R2 over S. Here is our induced voltage. E1 is just going to be A times E2. Here is our primary current, I1. Here is our secondary or rotor current referred to the stator, I2 prime, which is just our rotor current at the rotor divided by A. And I'm going to throw a dashed line right here to let you know that everything to the right of this line is the power transferred across our air gap. All right, so there is one thing here that we have yet to talk about with regard to induction motors. Quantity A. So in a transformer, what did A represent? The turns ratio. Absolutely right. In an induction motor, A also represents the turns ratio. So the turns ratio of the stator compared to the turns ratio of the wound rotor. So technically this doesn't work for a squirrel cage system, but we can have an effective turns ratio, which the overwhelming majority of the time is 1. Yeah, so it makes life easy. We don't have to do anything to refer stuff from the rotor side to the stator side. Okay, so I do have one last thing I want to talk about here, but this is not the equivalent circuit that we are going to wind up using. Okay. So in class on Thursday, I'm going to develop a different equivalent circuit that will be easier for us to use. It is not going to be the cantilever equivalent circuit that we dealt with for transformers. It actually can't be, okay? The reason that it can't be is, if you recall, we were able to lump all of our leakage resistances and reactances together because our magnetization current was small, typically between 1 and 5% of our primary current. Our magnetization current in an induction motor is going to be 30 to 50%. So effectively, we can't just move that shunt stuff over to the primary terminals and call it a day. So we're going to use Thevenin equivalent circuits in order to make our life a little bit easier. All right. But before we do that, the last thing that I want to talk to you guys about is power and efficiency. And this is kind of a high level view of things here. Like I forgot the I. So we're doing a high level look at things right now, just because once we get our Thevenin equivalent circuit, we'll bother with the math and things like that. Okay. So all I'm going to draw here is a power flow diagram. All right. So on the left-hand side, we are going to have our input power. So this is the electrical power delivered to our stator. Okay. So because we have stator windings, we are going to have stator copper losses. Should make sense. And P1 CU, because this is on the primary or stator side copper losses, this is going to be nothing more than 3 times the magnitude of our stator current, squared times R1. 3 because it's a three-phase system, I squared R losses, nothing wild or crazy there. So our stator copper losses take away some amount of the total power. Now we also have our core losses, P core, and we could look at our equivalent circuit and figure out how to do that, but we're not going to worry about it because that's going to be something that we measure with one of our open circuit, short circuit, block rotor, no load kind of test things. Okay. So at this point, these are our losses in our stator. And so we've now hit our air gap, right? So at this point, everything that's left is power delivered across the air. So now we're on the rotor side of things. Our rotor either has windings or is made of electrically conductive material, and so there are going to be copper losses there as well. Bless you. This is P2 copper, not giving you the equation again because I gave it to you a few moments ago. And then everything left after our copper losses is our mechanical power that's delivered to the rotor. All right, but we still have losses to take into account. So for instance, there are going to be friction and windage losses. So effectively what friction and windage losses are is if we have a wound rotor, there's going to be friction between the brushes and the slip ring that is going to cause some power to be lost. Additionally, we have to consider the fact that we have a rotating system, so there's air resistance that needs to be taken into account as well. So that's all lumped together as friction and windage losses. PFW. And then lastly, we have a loss here called stray losses. P stray, where these losses represent any other losses that we observe that we can't attribute to anything else. Typically, they are negligible, but including them. And now finally over here on the right-hand side, this is the power that's delivered to the shaft of our machine capable of doing work, or our output power for our system. Okay. So as you can probably guess, our efficiency N is simply going to be our shaft power divided by our input power. And we can actually also develop a couple of simple torque relationships here. So the torque that is delivered across the air gap effectively, or the delivered mechanical torque, I guess would be a better way to put it, is the mechanical power divided by the angular velocity of the rotor. Since the mechanical power is nothing but the air gap power times a factor of 1 over S, and the angular velocity of the rotor is nothing more than the synchronous velocity of the rotor times a factor of 1 over S. This is nothing more than the air gap power divided by the synchronous angular velocity. The output torque is the output power divided by the angular velocity of the rotor. And we could also write this as the power delivered to the shaft times the angular velocity of the stator times a factor of 1 from this test. All right, I have an example problem, but we have 6 minutes to work it, and I don't think that's enough time, so we'll probably kick things off with that. So we're knocking off a couple of minutes early today. I hope to not talk for the full 2 hours on Thursday, so we shall see. Yes, ma'am. About you not being on class?
Yeah.
On Thursday? Huh? Yeah. Like, I appreciate you letting me know, but I really don't need to like see an excuse or anything like that, because I forget to take attendance most days anyway. So, yeah, like I genuinely do appreciate letting me know.